Hello friends, next we start the second law of thermodynamics. As you know, the first law of thermodynamics only tells about the possibility of conversion of heat into work, but it does not tell what fraction of heat can be converted into work and what will be the direction of the heat flow. In order to explain these two things, second law of thermodynamics came into being. There are two main statements of second law of thermodynamics. One is Kelvin-Planck's statements of second law of thermodynamics, and second one is Clausius statement of second law of thermodynamics. First we discuss the Kelvin-Planck statement of second law of thermodynamics. It states that it is impossible to get a continuous supply of work by cooling a body at a temperature below the coldest of its surroundings. That is, no engine can work continuously by keeping its temperature below the coldest temperature of the surroundings. This statement explains the working of a heat engine. You know, in any heat or in every heat engine, the temperature of heat engine during working is always greater than the temperature of surroundings. Next, this also explains that total heat cannot be converted into work, that is, efficiency of heat engine cannot be 100%. Second statement is Clausius statement of second law of thermodynamics. It states that heat cannot flow of itself from a cold to hot body. That is, heat will not flow from cool to hot body by itself. That is, it may do so if some external force is applied. So this explains the working of a refrigerator, where heat flows from a cold body to hot body with the help of external work done by the electric power. Next we take the Carnot's heat engine. It is a hypothetical engine which cannot be constructed practically because it assumes all the required things to be perfect. For example, in these diagrams, double or thick walls represent perfectly insulating walls, and thin walls, this represent perfectly good conducting walls. Here, working substance is ideal gas, which is perfectly ideal gas. This is perfectly insulating stand. It has four parts shown by 1, 2, 3, 4. First part is a cylinder fitted with a perfectly frictionless piston which contains an ideal gas as working substance. Second one is the source having constant temperature T1 and infinite heat capacity. Third one is perfectly insulating stand, and fourth one is sink at lower temperature T2 having infinite heat capacity. Now the working, we consider the working. Step 1 is isothermal expansion. First of all, working substance cylinder means one is placed on source 2 and slowly expanded at constant temperature T1. because the heat capacity of source is infinite, therefore its temperature remains constant. Thus, at constant temperature T1, working substance draws heat Q1 from the source, and that is the process will be isothermal expansion from A to B. At point A, pressure is P1, volume is V1, temperature is T1. At point B, pressure is P2, volume is V2 and temperature is T1. This is isothermal expansion. Means A1 is placed on 2 and gas is slowly expanded at constant temperature T1. During this heat Q1 is drawn by the working substance from source. This is shown by curve AB. Curve AB of Carnot cycle or indicator diagram. Second step is adiabatic expansion. Step number 2 is adiabatic expansion. Now one is placed on 3. From here it is put here and again expanded suddenly till the temperature of gas becomes equal to T2. Thus the process will be adiabatic from B to C. So now one is placed on 3 means insulating stand, and gas is suddenly expanded. Till temperature T2 is reached. This is shown by curve BC of indicator diagram. Next, isothermal compression. Third step is, step 3 is isothermal compression. Step 3, isothermal compression. Now one is placed on 4, means cylinder is placed on sink and compressed slowly as shown by curve C to D at constant temperature. Now one is placed on 4 means sink, and gas is slowly compressed. Slowly means isothermally at constant temperature T2. Compressed at constant temperature T2. During this, heat Q2 is rejected to the sink. During this, heat Q2 is rejected to sink. This is shown by curve CD of indicator diagram. And next step is adiabatic compression. Fourth step is adiabatic compression. Step 4. Now one is again placed on insulating stand and suddenly compressed till the initial state A is reached. This is adiabatic compression. Now one is again placed on 3 means insulating stand and suddenly compressed till initial state at A is reached. This is shown by curve DA of indicator diagram. This completes one cycle of operation, and this cycle, closed cycle ABCDA, is known as Carnot cycle. Again I repeat the process. One is placed on 2 and gas is slowly expanded from state A to state B. During this, heat Q1 is absorbed by the working substance from source at constant T1. Now one is placed on 2 and compressed adiabatically till the sink temperature T2 is achieved, shown by curve BC. Now one is placed on sink and compressed slowly from C to D at constant temperature T2. During this, heat Q2 is rejected to the sink, and last step is adiabatic compression DA, from D to A. Again one is placed on insulating stand and suddenly compressed till initial state at A is reached. This completes one cycle of operation called Carnot cycle. Next similar cycles repeat. Next we take the efficiency of Carnot engine. efficiency is denoted by symbol eta and is defined as the ratio of work done to the heat taken from source. Means this W is heat converted into work, heat converted into work upon heat taken from source, So total heat Q1 was taken from source and Q2 is lost to the surroundings. So remaining heat Q1 minus Q2 is converted into work. So this is Q1 minus Q2 upon Q1, which can be written as Q1 upon Q1 minus Q2 upon Q1 plus efficiency eta will be equal to W upon Q1 or 1 minus Q2 upon Q1, and percentage efficiency can be obtained by multiplying it with 100. We can also find the efficiency in terms of temperatures T1 and T2. At from figure means indicator diagram. From indicator diagram, total work done will be, suppose you say W, so W from A to B, from B to C, from C to D, and from D to A. So W from A to B, W from B to C, W from C to D, and W from D to A. Now, if the amount of working substance is N mole, then from the cycle, therefore from the Carnot cycle, total work done W will be equal to, from A to B isothermal process, nRT1 log B2 upon B1. From B to C adiabatic process, nR upon gamma minus 1 T1 minus T2. From C to D isothermal process, nRT2 log B4 upon B3. And from D to A adiabatic process, nR upon gamma minus 1 T2 minus T1. Clearly these two terms are equal and opposite to each other and therefore cancel out, and first and third terms remain. Therefore W will be equal to nRT1 log B2 upon B1 plus nRT2 log B4 upon B3. Suppose this is equation 2. Now points B and point C, points B and C of indicator diagram lie on the same adiabatic. Therefore T1 B2 power gamma minus 1 at point B will be equal to T2 B3 gamma minus 1 at point C. Equation 3. Similarly, points D and A on indicator diagram lie on the same adiabatic. Therefore T1 B1 gamma minus 1 at point A will be equal to T2 B4 gamma minus 1 at point D. Now dividing equation 3 with equation 4, T1 cancels, T2 cancels, and we get B2 upon B1 gamma minus 1 is equal to B3 upon B4 gamma minus 1. Because the powers on both sides are same, therefore the quantities within the brackets will be also equal. That is, V2 upon V1 will be equal to V3 upon V4. Or reversing the, interchanging the numerator denominator, we can write it as V4 upon V3 equal to V4 upon V3 is equal to V1 upon V2. Now this substitution may be made here, means in place of V4 upon V3 we can write V1 upon V2. So equation 2 can be written as W is equal to nRT1 log V2 upon V1 plus nRT2 log, in place of V4 upon V3 we can write V1 upon V2. V1 upon V2. Next, equation 2, 3, 4. Suppose this is equation 5. Equation 5. Also from indicator diagram, from A to B. First law of thermodynamics gives dq is equal to du plus dw. That is, from A to B, dq is q1, du is ncv dt, and dw is wab, because dt is 0 for isothermal process. Therefore, this becomes 0 and we get q1 is equal to w from A to B, which is nRT1 log B2 upon B1. Suppose this is equation number 6. Now with equations 5 and 6 we get efficiency. Therefore, from 5 and 6 we get efficiency as W upon Q1, which is W means this much, nRT1 log B2 upon B1 plus this. When you interchange the numerator and denominator here, you will get minus sign here, because log A upon B is equal to log AB. So you can write here nRT2 log B2 upon B1. Here numerator and denominators interchange, therefore we get here negative sign instead of positive sign, and Q1 is nRT1 log B2 upon B1. Now nR log B2 upon B1 is common to numerator and denominator, therefore we get eta is equal to W upon Q1, which is equal to NR log B2 upon B1, here T1 minus T2, and here NR T1 log B2 upon B1. So NR log B2 upon B1 cancels out and we get 1 minus, means we get T1 minus T2, T1 minus T2 upon T1, which is 1 minus T2 upon T1. Thus, eta will be equal to W upon Q1, which is 1 minus Q2 upon Q1, or 1 minus T2 upon T1. Thanks.